Welcome everyone to the March Meetup. First off, is this anyone's first time here? I see a lot of returning faces, but also some new ones. That's awesome. Welcome. From there, first thing we like to do is anybody in the room hiring? Anybody have open positions they want? Brilliant. Do you want to come up, grab the mic, and tell us about it? Cool. And if you can stand behind the podium as we
Hi, everybody. My name's Noam Ross. I'm Executive Director of the rOpenSci project, but I'm actually here hiring for another project of mine called Grant Witness. Grant Witness is an organization that is tracking changes to federal science and public health grant making and spending, tracking terminations, accounting changes, how federal agencies are changing where they're doing. We are hiring right now for data scientists to join our team that primarily does work looking at forensically at federal spending and activity databases and trying to identify how the federal budget is changing. And this information goes to journalists who are writing about this work, activists who are doing science and public health advocacy, and a great deal to litigation and court cases that are being brought against the federal government for taking away funds in public health and science. It's a small team. It's an intense and very impactful project, and we are hiring right now. We're probably going to be reviewing applications this weekend, so it'll be you'll want to get something in fast, but please come up to me at the end of the talk if you want to talk about it.
Great, thank you so much. That sounds like a super cool gig. Anybody else? Okay, cool. I'm actually, my company is also actually hiring. So I work at Grow Progress. We're a progressive research organization that helps advocacy orgs, PACs, nonprofits. We're also growing a commercial side of the business, do a wide variety of types of research that help inform how they do their advocacy. So this is everything from polling to survey RCTs to understand which ads are effective. And we're hiring for a role called a research strategist. This is sort of a role that sits between our data science or more technical teams and helps clients plan out research agendas that make sense for their products and helps them inform how they do their work. So if you like working with people and you like having some insight into the, what's the best way we could plan out this research, it's a great role. If you're here tonight, feel free to come up and say hi. I'd love to chat about it. It's in the Slack already with the job posting. Yeah, I think that's what I've got on that. Other than that, pizza tonight is from Bravo Pizza, which is actually a repeat for us, which I learned from Nicole as of 6 years ago or something like that. So if everyone can pull out their phone and go to bit.ly/pizzapoll and rate the pizza for us, we can start developing a pizza quality over time model with this. Tell us how it went, vote on it, help build Jared's data set that I forgot to mention last time. bit.ly/pizzapoll. LY. Cool. Also, we actually have the next 2 meetups planned already. April 16th, we'll have Muskin. She's talking about stress testing generative AI in high-stakes policy situations, which sounds great. And then in May, we have Christian, and he'll be talking about a unified R interface for NYC open data APIs, which also sounds really cool. April 1 will be posted soon, so come check it out. After this, we'll be going to the bar. Even if you're not here in the room tonight, you're welcome to come after the event and join us. We're going to White Oak Tavern. It's there. If you get lost, I don't know what to do about that. Okay, cool. Thanks so much. You couldn't be here tonight, but George Perrett from NYU for hosting us. Thanks to him, we get to have this lovely space and be in the same place every week. Really appreciate him. And now we get to introduce our speaker for tonight. I'm super excited to introduce Jason. Jason is an assistant professor and associate director in the Data Science and Information Systems Department at the City University of New York at CUNY. Cooler for this group, though, he maintains over a dozen R packages, which is wild. So yeah, everybody welcome Jason.
Thanks, Andy. Really appreciate it. So yeah, I'm going to talk about cluster analysis, and I know there's been a lot of AI talk, so the only AI bit in my talk is this hex sticker that I used, Nano Banana to create. I just actually threw this in at the last minute. So I don't know, everybody's heard this quote, right? There are two hard things in computer science, cache invalidation and naming things. So I was trying to come up with a clever name for this talk. And so, you know, happened to be in the grocery store. I was like, oh, Special K cereal, right? And then my colleague who's here mentioned, oh, that's also a drug. So I really didn't mean to talk about the drug, although at the end we may want that. I don't know, or at least we'll get beer across the street. So this is a little overview. I need to acknowledge that this work is supported through an IES grant. I really love the work that our OpenSci is doing in tracking this. I follow you guys on Mastodon. I think it's really important. I'm one of the lucky ones that my grant wasn't terminated, although the department for which my grant is run through went from 140 program officers to 2. So, you know, it's really sad what's going on at the federal level, but this work is supported in part there. So the grant I have actually is to build and test something called DAACS, or the Diagnostic Assessment Achievement of College Skills. What we built is sort of an alternative to a college placement exam. So we assess students in self-regulated learning, reading, writing, and mathematics. Students receive immediate feedback in terms of 1, 2, or 3 dots. They're developing emerging mastering. They get links to open educational resources, strategies, and the like, right? So we're wrapping up, we're in the last year of our grant, so we did a large-scale randomized control trial at the University of Albany, University of Maryland Global Campus, and Lehman College, which is part of CUNY. And I'm happy to say, in terms of the large-scale RCT, we found that indeed students assigned to the treatment group actually had a higher GPA in their first term than those in the control group by about a half a letter grade. So this is something that takes students about an hour to 90 minutes, and we embedded it into like a first-year course. But of course, we've been looking at using this data to build predictive models because we're trying to identify students at risk so we can provide targeted resources. And so one of the things my colleague and I, who's at Rutgers, have started looking at is like, can we build profiles about students so that we can create buckets of tailored interventions to where students are? And so of course, we're looking at cluster analysis as a way to do that. So this started here about a year ago, and I got some outcome measures. Now, no one's done cluster analysis, right? This falls under a class of what we call unsupervised methods, because generally we don't know what the true clusters are, and we're going to try to estimate that and make profiles, okay? Versus a supervised, where we know when we do predictive modeling for student success, we observed whether or not they pass or fail or what have you. And so the general steps for cluster analysis is, obviously first you got to determine the number of clusters, and then you want to do some kind of validation. And I started digging into the literature, and it's what I'm going to present tonight. It's a bit of a mess, I would say, in terms of figuring out how to do it. Okay, because I am a teacher, I can't resist. If you're not familiar, I'm going to talk about 2 key clustering methods. There are a lot. I would like to include more, but I'm going to keep it. But the 2 most common is k-means clustering and hierarchical clustering. Okay, so I have this little animation here that is kind of showing. So the way k-means clustering works is we generally randomly select k clusters, right? K observations, and then we find the observations that are closest to that cluster center, assign it to it, and then move this cluster centers to the center of those assignments. And so that goes iteratively. So in this example, looks like it took about 11 iterations before we get to the final cluster solution. Hierarchical clustering, on the other hand, sort of starts and presumes every observation is its own cluster. And then you create a distance matrix, and it's going to start combining clusters. So the way this is set up here on the right-hand side, gray points are observations that are in a cluster by themselves, and I start to color them, and you can see as k is going down, and we're kind of reducing it. If you want to play around with this some more, I'm not going to spend a whole lot of time, but I do have a Shiny app that allows us, you can kind of go step by step, and you can see these things. So particularly if I go to hierarchical clustering, right, it starts, there are 332 observations. But, to me, the most interesting is when you get down to the last few as k reduces, you can see how these kind of clusters start to combine to the desired k. Okay. Okay, so a lot of what I'm going to talk about is I started putting together a bunch of resources. This started as a way of trying to validate, because really what we want to do is develop a cluster profile at one institution and be able to apply it to other ones, or develop at one institution and kind of validate it. But then how do we do that? So this is in a package called CLAV. Again, hard problem naming things, so I'm open for suggestions. It's not on CRAN yet, so I still have an opportunity to rename it. If you look at the hex logo that I have on the GitHub site, I like clavinets, I like music, so I thought it was short, but it's cluster analysis validation. In terms of DAACS, I'm going to digress in a moment, but these are the variables I'm looking at. So under self-regulated learning, we have motivation, metacognition, and strategies, or sort of high-level domains. Then, of course, we have reading, writing, and mathematics, sort of as a college readiness. So these are freshmen. In terms of outcomes, we have feedback views, which is sort of a proxy for engagement, if you will. So because students can navigate the website, look at stuff, so we track their clicks. And then we have term success, because this was at an online institution, so this is whether or not they were retained for a second semester. One of the reasons why we're particularly interested in this is, so if we look at this from a variable-centric point of view, and I'm sorry if this is a little small, but I'll point out a couple things. So on the left side, I'm predicting feedback views from all of those variables. On the right-hand side, I'm predicting term success. So left is a regression, the right side is a logistic regression. A couple of things that have been bothering us for years is, one, metacognition, right, which is thinking about thinking, is negatively related to, in this case, feedback views and term success, meaning students who are more metacognitive are doing worse. And that's been sort of a question for us for a while. And there's a few other things that kind of get problematic. So I started digging in. It's like, okay, great. I don't know how many clusters I should have. And so I found 6 kind of common metrics people use depending on different domains. The reason why I would like to do that little digression about how k-means works in hierarchical clustering, because some of these methods might work better than others, right? So k-means in particular, as we see, is going to presume that the clusters are spherical, right, in nature. A hierarchical cluster may be a little less so. So these are some of the common metrics that we have. I'm not going to go into great detail, but if the slide deck will be up later, there are links to, I think, the Wikipedia page for each of these. The referencers are here. But what I've done to kind of simplify this for myself and my colleagues is I wrote a function called optimal clusters that takes my data frame, takes a max k, so I'm not going to consider more than 6 clusters, and I give it a cluster function. So I'm just going to start with k-means for the moment. This is the summary table, but I think the plot is a little bit more meaningful. And even to help myself, to remind me, I put in the subtitle what the desired outcome, right? So for Davies-Bouldens, we're looking for lower values. For Kalinsky-Harabasks, we're looking for higher. Within sums of squares, which is probably the most common one, we're looking at this elbow approach, which to me is really challenging to figure out where that is, which is why I added these kind of horizontal lines, because sometimes it's, to me, a little bit easier to visualize where the lines are a little bit closer to find out where that elbow is. Okay, but for us, right, I'm looking at this. So here, lower values, so I could say, well, 6 technically is the lowest, but 5 and 3 are close. Higher values, so the Kalinsky would tell me I should have 2 clusters. Who knows with the within sums of squares? Silhouette, probably 3. Gap is either 1 or 6, which is kind of interesting. And the RAND, sort of, you're looking for flatness, so I'd probably say 4 is probably the ideal. Okay, the point is, they're all different. They're telling me a different number of clusters. And so this is where I was with my colleague. It's like, okay, we're working on this. It's like, there's no agreement. What is going on? And so this is where I, about a year ago, went down a massive rabbit hole in trying to figure this out. And so to do this, I went to our 2 classic cluster analysis data sets, Palmer's Penguins and the IRIS data set, mostly because the cluster assignment is known, right? So now I have a known outcome, so I could start exploring. So this is just my data set up for how I'm going to use it. Of course, I'm scaling everything to be standardized. Here's data visualization. So they're both 3 cluster solutions. So here's another thing I'm going to ask you guys. If you have other cluster or data sets that are something other than 3 that I should be playing with, I would love to know. There's some synthetic data sets I found, but I would prefer more authentic real data sets. All right, so let's go. So I'm going to look at k-means and both hierarchical clustering. So here on the left-hand side, I'm using k-means with the penguins and k-means with the iris. And then I go to the hierarchical clustering, and I'm just going to go to the summary table to look at it here. So 3 is our ideal target, and if you want to go, we can look at this in detail, but you can maybe take my word for it. This is what I would determine the optimal clusters would be. So, in the case of hierarchical clustering with iris, none of the metrics get it right? The best case scenario is k-means with iris is at a point, half of them would identify. So 3 of the 6 metrics would result in the optimal number of clusters. So this is not great. I'm going to kind of go to the end and then work my way backwards, because this is kind of how I encountered it. So we were first kind of interested, and I'll explain a little bit how we came to what our desired clusters are for the DAACS data. But really what I was looking at is this notion of validation, right? So, okay, the K is a bit of a problem, but really what we want to know is if we define a particular cluster profile, is it stable, right, across a bunch of data sets? And so one way to do that, right, so Ullman et al. is a nice paper that I think was arguing for the use of a visual approach. And anything that's visual is really appealing to me as a way of kind of arguing it. And so they argued that you split your data set in 2, right, in one way. So on the left side is a training set. On the right side is a validation set. Insofar as what I'm doing here is I'm training the k-means on this training set, right, which is 50%. I did a 50-50 split. And then I'm predicting the clusters with the validation set on the right side. So I'm only using half my data. And, right, so they would say, you look at this plot and say, do the profiles look roughly the same across 2 separate data sets? You could alternatively just train 2 cluster analysis with 2 different data sets and see if it exists. I thought this was interesting, but I thought maybe we could do a little bit better. And so I said, well, what if, depending on how I draw the random samples could have an impact, right, if I pick a bad one. So what if I just do lots of random samples? And so the cluster validation turned out to be the first function I wrote. And so I pass in a data frame. I'm assuming 3 clusters. We'll come back to figuring that out later. I give it a cluster function, and I'm going to sample 50% with replacement. And so by default here, I'm going to do that 50-50 split 100 times. Now there's a parameter, you could do it 1,000 if you want, but I think 100 is enough. And the dark blue lines you see on both sides is what the cluster profiles are if I use the full data set, and then the other lines are showing it with a 50% each time. So on the training set, I'm going through, and as a precursor or kind of foreshadowing what I'm going to talk about in a minute, I called it an out-of-bag sample, which is the other 50% for now. And I'm predicting the out-of-bag from the training set. So what we have here is, so we have bill length and flipper length. And so what Ullman et al. Were arguing for is, well, because these are stable across both data sets and here across many data sets or many simulated data sets, that we could say that it's maybe argue that it's a valid profile because there's at least stability and consistency across the 2. So if we take those distributions, so this plot here is a plot of the means, right? So what these values here on the edges is the mean for each cluster for each variable, right? So this is bill length. If I had a 3 cluster solution, so I have 3 clusters, and so these are all the centers. So I can plot the distributions, which is actually kind of helpful in terms of deciding what variables to include. So I could see, if I start with flipper length, for example, in general, the clusters have pretty good separation on that variable across all 3. But for bill length, for example, cluster A is sort of separate, but B and C have a little bit of intermingling going on, okay? Hard to see a little bit when I'm only using 2 variables with the Palmer's penguins, but when we get to the DAACS data and I have 6 variables going into the cluster profile, it starts to tease out which variables are really important in terms of determining cluster management. So from here, I said, well, maybe we can do a little bit better. We can use the good old bootstrap, right? So instead of just doing 50-50, I can actually take bootstrap samples. And it turned out I didn't really have to do much except change my parameter functions. Once I implemented it for the 50-50, I just had to add, here I'm sampling the number of rows of my penguins, and I'm adding replacement. And so again, I'm training, either doing k-means or hierarchical clustering, and then predicting the cluster management or the cluster membership from the out-of-bag sample. Okay, small digression for anybody who's interested in using this implementation note. So I want to give praise. He's probably not here, but like what Max Kuhn and his team is doing with tidy models in terms of common interfaces. I thought about using tidy models, but I didn't want to have that dependency. But it seems like all the clustering functions implement them very differently in terms of parameter orders, and hierarchical clustering, for example, doesn't have a predict function. There is no predict function. So if you want to use this package, I sort of have a couple of rules, and basically the rules are make your function behave like k-means. So for k-means, the first parameter is your data frame, and the second parameter is how many clusters you want, and then you have to have an S3 method for predict that takes an object and optionally a new data. So very likely the predict function you could reuse. I'm just doing closest using a Euclidean distance, whatever which cluster center is closest, right? There are other ways you can do it. There's different distance metrics that you can use, but for simplicity's sake, I'm just doing that. So you could probably reuse this slide. If you're going to do hierarchical clustering, I call it hclust2, is just in the clav package, so it'll be there for you. I'm working on an implementation for latent profile analysis, which is another popular approach. So I might add more as we go along. But anyways, small implementation detail. So from here, I started thinking about, are there metrics I can introduce with these bootstrap data that might help me identify K, right? So I started down this path in order to kind of figure out if my cluster profiles are consistent or stable. But now I have all this data. And so I'm proposing here, and this is fairly new, 2 fit statistics from this. One I'm calling a cluster overlap fit. Since I have these distributions, I'm going to go back to this slide, right? So I have a distribution of the means. So I have these density distributions, so I can easily calculate the percent overlap for 2 different distributions across all of the metrics. So that's my first measure, right? So obviously a smaller value is desirable, right? I want more separation across all those variables. So that's what the overlap fit does. And I can look at it for 2, in this case, 2 to 6 clusters. So there's a lot going on in this plot, for sure. I tried to color, so it's color-coded by variable. And then obviously you can see as I get to 6 clusters, I have, 6 clusters for 2 variables. So I guess that would be 12 points, I think, in that, if I'm doing my arithmetic correctly. So, and then I have this line here for the median overlap, and the green line is the mean overlap. And then, oh boy, I'm drawing a blank. I can't remember what the error bars are doing. So I'm using this as a notion, say, okay, smaller values are ideal. So in the case of penguins, if I just use the median at 3 clusters is 0. So that seems pretty decent. But again, as we're going to see, I think with cluster analysis and why I have in the title, there's a little bit of art going on here. So, I might be rationalizing this because I know it's 3, but that's what we have. On the right side, I'm using hierarchical clustering, and we kind of have some stability here. But what's also interesting is you can always go in and look at these clusters here and these variables. So this is 4 here. actually we could look at this. 3 is the bill length, and I think it's the right, it's that one. Basically, we're seeing the overlap between these two distributions here. So that's okay. And then we can do the same thing for the iris data set. The second one I sort of started to think about, and I have to give credit to Kelly Bodwin, because I met with her last year at PositConf, and we had a conversation about this after a talk I gave there. And she proposed, like, well, what would be interesting is how well do each observations agree with its neighbors, right? And that's really key, right? If I'm going to be assigned to this, even if the cluster seems to move around, if I'm always being clustered with the same observations, then that would be a good thing, right? So I call this the cluster agreement fit. And so what I do here is for each bootstrap sample, I'm looking at the cluster membership, and I want to say, okay, if I'm person A, am I always in the same cluster as cluster B? And so I want cases where it's always 0, I either always want to be in the same cluster or never in the same cluster, right? And so what ends up happening is you get a few observations or some observations, and they're generally on the boundary that have some disagreement, right? They bounce around. So that's another bit, and the next step, sort of future direction I'm looking at is, can I use that information and create boundaries around the clusters where I could say, well, if you're in this range for these different variables, you're very likely in this cluster, right? Have a high probability, and then here's some other, in between where you could be A or B, right? Maybe have some predicted probabilities along with this that don't exist currently. So here, again, I'm looking for higher values. On the left, using k-means, on the right, h-class, hierarchical clustering again, still trying to figure out there's some, it's kind of flat, right? Although it gets better as you go up, which kind of makes sense, whereas for k-means, it seems to get worse as you get larger. This is interesting because here, what I'm looking at is all of the observations. So I have these kind of big bars at 0 and 1. That's actually desirable. That means I never am in the same cluster as this other observation or always. So what I'm looking for is like what's in the middle, right? And you can see here, once I get to 4, right, I have almost no, there's like no, I'm either never or sometimes I'm in, right? There's a lot of like overlap, which in some ways makes sense because the more clusters I have, the more, they're kind of going to bunch up against each other. And so I have more boundaries and more places for things, for observations to kind of bounce around from cluster memberships. And then the iris data set kind of shows a similar thing. Okay, so coming back to DAACS, what did we decide? So if I look at the overlap fit here, in terms of median, right, I go all the way out. I should also mention that this particular DAACS data set has about 6,000 observations versus a few hundred for the iris and penguins, okay? I'm also using all 6 variables. I recognize that for iris and penguins, there are, I think, 4 for each of them that I could potentially use. In my little playing around, it didn't really make a big difference, and having only 2 makes it easier to visualize things. So in terms of these, we ended up deciding on 5 clusters as our optimal solution, looking at all these variables. And I'm going to be honest, some of this feels like I went down this rabbit hole. Some of this was useful in terms of determining which variables are important and understanding what's going on. Some of it feels a little like rationalization, right? But this is, I'm trying to share what I found. In terms of the validation, I do think there's some promise here, right? Having this, using the bootstrap samples, and so using this, I could see there's quite a bit of stability across all of the bootstrap samples. And similarly, looking at these distributions, even though some of these fits seem a little odd, we could see, like, for reading, we actually know this about our reading comprehension. It's a highly skewed distribution, and in terms of if we convert it to a 0 to 100 scale, probably 85% of students score a 70 or better, right, would be the passing. But for those students who score below a 70, their likelihood of success in college is extremely low. So it's still a really important discriminator, but violates a lot of at least the parametric and frequentist approach to modeling. So we see that here. So of course we see a lot of overlap there. So there's a lot of like little bits here that we need to consider that, yeah, there's separation in one cluster and not the other. So of course that's going to make the overlap fit seem a little bit higher. So I'm considering like maybe I need to separate this out by variable and what have you. So I want to get to the art bit of this, so I need to go over here real quick. And so when I say art, this is what we spent a lot of time doing. So I built this little shiny app, and what we ended up doing, right, so I could change these Ks, right? So this is definitely the art bit. So we went to, I kind of don't want, well, this is going to take a second to run, but if I click the tab, I think it'll run in the background. So I started with just the within sums of squares. This will come up with my optimal K thing, right? I could add and remove variables. Oh, I have feedback views. I need to take that out. And so this is a shiny app you can use if you find yourself needing to do cluster analysis. So a lot of what we did is kind of looked at this. Oh boy, this is the problem with live demos. I can go back to here. This is what I wanted to look at. So this is a profile plot. So ultimately, this is what we wanted to say about our students. So on the right-hand side are, here are 6 variables going into the clusters. We just landed on K, and we could see where the variables are. And then on the right side are our 2 outcome variables by cluster. And so we can kind of see an interesting relationship. So what did we learn? A couple of things I added to this is I think this green band is accounts for about 50%. I think it's like the interquartile range, right? And so we use this as a threshold to say students within or scores within that are like within the mean or close enough to the mean that we call average. Anything above we would call above average. Anything below is below average. That was just the way we wrote it in the paper. So a couple of things I want to point out. One is I think now have a theory in terms of like why is metacognition negatively related to success, despite everything in the self-regulated learning and learning literature to say the opposite. And it turns out, right, if you look, we have some students, right, who are low self-regulated learners overall, or at least self-report, and we have some students who are high self-regulated learners. If we look at the high ones, they're actually not the highest performing academically, right? So these are students who probably are a little maybe overconfident or overestimating their learning, their self-regulated learning skills. Similarly, the students who are the lowest in the self-regulated learning are average academically, right? So our hypothesis at the moment is that there may be like a calibration issue, right? Because the self-regulated learning, these 3 variables are self-report, okay? And in particular, if we look at like motivation to metacognition, we have a bunch of these clusters where there's like this crossover. So there's 2 theories. One, they're miscalibrated. The second is they're misinterpreting the measure or the questions that contribute to that measure, right? We talk about metacognition, we talk about planning, monitoring, evaluation. Maybe some students are overstating or understating, so their abilities are there. So we're starting to kind of get some understanding. If I don't have it presented here, if we use the cluster assignment now in our predictive models, these clusters become significant predictors, right? And why this is useful to us, even though whether or not we picked K 4, 5, 6, 1, is that now, at least from a learning theory point of view, we have profiles that explain possible different interventions for our students. So for example, as I mentioned, that reading, right? So we have that cluster that's mostly defined by students who score really poorly on the reading comprehension. So the interventions we're going to do for those students are going to be different than all other students, right? And some of this is like we have students where English is a new language, right? So those kinds of interventions. We have students who think they're really good self-regulated learners, right? They tell us, I use a planner, right? I manage my time very well, but academically suggest, maybe not, right? So talking to those students is a little bit different. I don't know if there are other teachers here, if you encountered other folks who are like, you know, I got this, and you go into that test and you fail, and you're like, whoa, how did I fail? Right? You think you managed your time well, but maybe not, or you studied well. So in terms of like practicality, this is turning out to be somewhat useful. Let me see if my, came up, awesome. Okay, so I kind of want to show a little bit of what we did. We spent a huge amount of time looking at, I got to define my dependent variable as, let's say, term success. Well, you could look at the pairs plot, which is from the GG pairs. I think it's the, of course, I should have taken screenshots. Essentially, we went through and adjusted the K, and this is where that art piece comes in quite a lot, where because a lot of the measures said 4 or 6, we were between 4, 5, and 6. 3 we felt was too few, and it wasn't, you know, and as we extracted things, we were looking at the histogram in terms of cluster sizes, and a lot of the metrics like 5 and 6 was roughly the same. And when we look at this profile plot and how things separate and how we can understand our dependent variables, that 5 seemed to be the sweet spot where we had enough subdivision to say something meaningful from a theory point of view, and we felt like the statistics were kind of backing it up to a certain extent. So, you know, so the Shiny app is there for you to use. I found it extremely helpful. My colleagues found it really helpful who are more the theory folks, and I was the statistician. So this, I'm not going to go into a lot of detail on this, but you can adapt this Shiny app for your own data set and easily deploy it so that your colleagues can go in, you can change the number of clusters, look at all the different components, and really, ultimately, I think what I learned from doing this is you got to take all the information from all of these different methods to find the sort of combination that gives you the most explanation and the value as you go through. So that's kind of what I've been working on in terms of cluster analysis. This QR code will take you to the GitHub page. I do have a package down site there. The slide deck is up. It'll also be on the nyhackr, and I'd love to take questions or other questions.
And for the folks at home, if you have any questions, you can ask them in the chat, and we'll be able to get to those. Over to you.
Yeah.
More of a commentary as
Sure.
As an evolutionary biologist, the Palmer penguins data set is lovely but weird.
Yeah.
In the sense that I don't think 3 is necessarily the right answer there. In that there are 3 species.
Yeah.
They're all very closely related.
Yeah.
One of them is big. 2 of them are small.
Yep.
One of the ones that's small is the distant relevant.
Yeah.
One of the small ones and the big one are closer relatives. There's some ecological differences. The big one is a weird, fast evolving, like, oddity.
So-
Right? So like, I don't know that, like, we know that the answer there is 3.
Really? Okay.
So you've got Gen 2 and Chinstrap.
I'm an educational psychologist and statistician, so I,
Closely related things where 2 of them are evolutionary close to each other.
yeah.
A different set of 2 are morphologically close to each other.
Okay.
I suspect there's something like this going on in the iris data set as well.
so I'm sorry, I was supposed to repeat the question or comment, which is really that 3 clusters for Palmer's penguins may not be appropriate from a biological point of view.
I mean, it's one of those things where biology is 2 correct? Sure. Is 3 correct? Sure. Like, you know, like there's...
So you're just like, it's that art piece again, right? There's a lot of subjectivity in this area.
There are 3 things there, but they are not 3 equally different. Like, they're not equally
Yeah.
whatever things. So, I don't know how that affects, like, what you're doing, but, like, they're weird.
Yeah, well, I glossed over a lot. I found the iris to be particularly troubling in terms of, like, it was all over the place in terms.
I don't know the iris data or the iris species as well.
Yeah.
I suspect there's something weird going on there.
And I know, and I had conversations, I should acknowledge that there are some, people have some ethical concerns about the use of, it was originally published by Fisher in the Journal of Eugenics, so I want to acknowledge that, but, real data sets where we think we know the number of clusters, and now you've got me questioning even that, so, it's in all the textbooks. I got to think on that. I don't,
So in reference is between 2 and 4.
So Adderley and Chinstrap are small, but not the most closely related. Gen 2 and Chinstrap are small and big, but are the most closely related.
So 2 or 3.
I teach with this in a more evolutionary biology context. I think the metrics mostly give you 2, and I think for the data, that's kind of right.
Yeah. Okay. Well, let's. Now I'm curious. So I have all this here. So in k-means, here's penguins. If we go to penguins on the left for k-means. So Davies-Boulden would agree with 2. Kolinsky would agree with 2. Within group sums of squares is probably 3, I think. 2 for silhouette. Gap is 3. Rand is probably 4 or 5. So we're still kind of where, like.
Could you show your metrics?
Oh yeah, sure. Yeah, I don't know if I want to show that now, but so the cluster agreement fit for penguins on the left. Oh, this is both penguins. So certainly 2. The overlap is where I started. I actually think the agreement is probably a better fit statistic. I will say, I found it extremely useful to spend time looking at these distributions, right? To see where the cluster centers are, from a bootstrap point of view. Not so much here when I only have 2 variables, but when I had 6, I spent a lot of time staring at those figures, figuring out, and that also helps us to define what those cluster profiles are. It was really, really useful from that context. But here, so agreement, this is like, I'm looking at every pair combination. So by the way, this takes a long time with larger data sets to calculate, right? But I'm saying, okay, how often do I appear in the same cluster or not with every other observation, right? So, yeah, 2, but 6 probably using hierarchical clustering. But hierarchical clustering, I think, may not be the best approach with this data set because it does appear to be, the clusters tend to be spherical. So k-means is probably better. So anyways, I don't know. Another question.
Hey, awesome job. I'm going to get away from the penguins because I don't know anything about biology. Wonderful talk. Quick question. You mentioned that it takes longer for bigger data sets. About how long did it take in terms of the benchmark?
So he's asking about performance in time. So for the DAACS data set, which I think the N is a roughly 6,000, I'm going to say to do this, in the order of a minute, okay? It felt like a long time as I'm building my slide deck. I use caching so I don't recalculate every time. I've made a few headwinds in terms of increasing the performance. There's probably a computer scientist that can help me find a more efficient way of doing it. But yeah. So, I mean, not like days, like measured in minutes, tops.
The Ullman paper, you mentioned that if you visualize it, you can kind of get a sense of it, but I thought that advice kind of runs contrary to looking at a visual and trusting your, how do you reconcile looking at a visual and thinking you understand it versus...
So the question is, how do you reconcile the visualization with whether or not it's valid, or that the consistent?
Like how do you, you run all these metrics so you can determine the right number of clusters or something. The visual giving you, how do you know the visual is not giving you a false positive?
Oh, visual given a false positive. That's a great question. I have been thinking about it, and honestly, I don't have an answer. What I didn't present, because the data is not public, I tried to use only data that I made public, which is one institution that we collected a long time ago. So we have many institutions now. So one of the things you can do, and I have it described in the vignette, is, so here I split, and it's all coming from the same institution. So I almost expect it to work out, but what you can do is define you could actually give it 2 samples instead of just 1. So what we have seen is I train on institution A, and then I predict with institution B, right? So they're samples from different populations, right? And that's ultimately what we want, right? If we think about dimension reduction, like exploratory factor analysis, like so we designed our own self-regulated learning assessment, and when we did that, we collected pilot data, right? And we did an exploratory factor analysis, said this is the factor structure. Then we went to another institution and did a confirmatory factor analysis, right? What the problem is maybe this is where I need to think, there's no, as far as I know, a confirmatory factor analysis for cluster analysis, right? Ullman just said, well, look at the picture. If they look the same, then you're okay. Or, I mean, I could do an ANOVA or something and say the cluster centers are they the same or not, right? That actually might be an interesting next step. So, I mean, and that paper was, I have the date, it's not that old. What was the year? I forgot what slide. That's Efron. 2021, that paper is only 4 years old. So this is still fertile ground for, and I think we're still trying to figure it out.
I wonder if you think there is, or there has been, I don't know about, any approach to visual inference with clusters. So in like regression visual inference, you simulate 20 distributions from the null model, you simulate the regression or model the real data, and you see if someone can actually pick out the real data. And I wonder if there's something like this in clusters, or if there's an application for it where you simulate from these different clustering approaches, and if someone can actually identify, right, the fit one relative to the noise or other ones. I'm not sure what it would be, but maybe in the case when you're doing that validation approach, that is essentially some kind of classification or something.
It's not exactly the same. So the question is, oh my God, I'm going to have a hard time summarizing this. Visual inference, whether or not to be, from a regression point of view, applied to clustering. I'm sorry for the remote people. I butchered the question. I don't know. I got to read into from the regression. The answer might be yes. What I ended up doing is I set a lot of this up and gave suggestions like, from the data and from what I'm reading, I think it's 5 clusters. And I gave it to my theory people, my theory colleagues, who is experts in self-regulated learning and that kind of stuff, and said, okay, this is what the profile would look like. And they were like, yeah, the literature supports that, right? That metacognition, that calibration issue. So I'm not, it's not exactly the same as what you're saying, but my content experts kind of picked it out and said, yeah, that the literature could support that. But I need to read about what you're talking about in visual inference in terms of regression.
I think it has the opposite thing than the confirmatory value. So rather than giving, here's the clustering, if you look at it, does it look right? You know, you give a pool of options,
Right.
One of which is right at some level, right? And see if it can be identified, right? So it has to be sort of rethought in an unsupervised context.
Yeah.
But I wonder if there's a useful approach to bring that to give the opposite. Like, would they give the same answer if you showed, here are all 6. Does one? Can you see the one that stands out theoretically?
That would be an interesting experiment, yeah. I don't know. It's an interesting thought. Well, and then I guess here, I saw your hand first. And then we'll go.
Have you considered extending this to expectation maximization, which is another clustering, approach? But if you're assuming empirically, expectation maximization seems.
I haven't looked into that one specifically. If you shoot me an email with your favorite art package, I would look into it. I haven't encountered that one. The next one I'm working on is latent profile analysis using the tidy LPA, only because in the educational psychology field, it's kind of coming up more and more. But I architected this so that it should be relatively simple to include other clustering methods. And so in the vignettes, I outlined that. I had that one slide. This implementation note slide where I just had to write a tiny wrapper around hclust in order to make it fit how I want it to behave, which is basically what happened is I wrote it for k-means, and I was like, oh, I should make k-means a parameter. And then I tried hclust and realized hclust just has its parameters in different orders for obvious reasons, because when you do hclust, the resulting object essentially gives you the membership for any k, right? It's kind of, where k means you have to give it a k up front and you only get for the results for that particular k. So
There's advantages to it in the sense that it actually constructs a distribution for each of the means.
yeah.
So it might give you better insight into separability and other maybe you can find other metrics that might be useful.
Yeah, that's sort of my next step, is to kind of get as many of, a handful more, I think 6 might be 5 or 6 different clustering methods, and sort of expand. Right, so I foresee this table kind of growing bigger, adding additional clustering methods, and if I can get additional data sets where the clusters are known, or I think known. Now I have doubts, but right, just this kind of honestly, when I started, because we felt pretty good about our 5 cluster profile, and then, like I said, this was a rabbit hole I did not intend to go down, but the more I go down, the more interested I am, and the more. So I'm still trying to figure out how to write this up. Is it clustering analysis is a mess? What are we doing, or is it? There's utility, there's definitely utility here in the way we're using it, but it's really hard when we don't know what, we don't even, the exemplars, as I learned tonight, may not even be as well known as I thought, right? So, you had a question, yeah.
Is there anything in the literature about combining methods where you use k-means where it's really obvious, and then when you get to those less obvious, you switch methods?
I could not that I found. I don't want to say no for sure, because I didn't read everything on this. Part of the problem, I think, is we don't know if the clusters are spherical or not. we do, because penguins and palmers, at least the way I saw them, they look, right, like k-means should be fine. But like the method that we choose is also determining on how the clusters go together. So I'm not even sure we could know, right? So ultimately, so the answer is I don't know. I don't even know if we could know unless we actually know the outcome. I think this is just generally a problem with unsupervised methods, right? So I could explain why, H-clus doesn't work quite as well for these because I know it, because I could see it. But if I didn't know that, it might seem to work fine, and I would be none the wiser. Oh, any other questions?
Going twice. All right, everybody give Jason a hand for his great talk. Cool. Thank you so much, everyone, for coming out. Next talk will be next month, April 16th. Hope to see you all there. That'll be up on the website soon. If you want to grab another slice of pizza, we still have some left. If you want to take a pie, we probably have enough pizza for that squinting over there. If any grad students are in the room, thank you for your service. We're going to head over to White Oak Tavern after this. I'll see you all right there, and even if you were at home, you can come. Thanks, y'all.